Welcome back! Now that we know the process for implicit differentiation, we can answer questions that involve first taking a derivative implicitly and then using that derivative to analyze a more complex situation. So here's a basic relation, x squared plus y squared equals 4. You might recognize that as the equation of a circle centered at the origin with a radius of 2. If we sketch that, we can think about any point that lies on this circle and understand that the tangent line at that point does certainly have a slope. But that slope doesn't depend only on the x value, because that same x value has another point on the circle down here, and that tangent line has a different slope than the one on the top. So the value of the slope of the tangent line depends not only on x, but also on y. So finding dy dx should result in an expression that has both x's and y's, and can be used to calculate the slope at any point on the circle that might be of interest. So as we saw in the previous video, to find dy dx, we start with the original expression and then take the derivative of both sides with respect to x, because we're looking for dy dx and x is the independent variable. So the derivative of x squared with respect to x is 2x, and the derivative of y squared with respect to x is 2y times the derivative of y, which is dy dx. And on the right side, the derivative of 4, which is a constant, is 0. Now our job is to isolate dy dx. So we can subtract the 2x to the right side and then divide by 2y. And we get dy dx is negative 2x over 2y. And we can simplify by reducing the 2's, and we get negative x over y. Now let's see what we can use this for. The next part of the question uses the same relation and asks us to find dy dx specifically where x equals 1, and show what this means graphically. As we showed a few minutes ago, the graph of this relation is a circle with a radius of 2, so something like that. And if you're looking for a place where x equals 1, here's x equals 1, you can see that there are two different points that have the x value 1. And the y value is not terribly easy to read off of there, but we can still acknowledge that there is some tangent line at that point and some other tangent line at this point. So to figure out the y value, we need to use some algebra. We have x squared plus y squared equals 4. So we'll plug in 1 for x into the equation and solve for y. With a little bit of algebra, we'll get y squared is 3 and y equals. We could write square root of 3. Most people can get that far, but look at the graph and you'll remember that there's actually 2 results for y. There's a tendency to forget the plus or minus here, but the picture should remind you that we're supposed to get 2 values, not just 1. So we have 2 points to work with. The way we indicate the slope at a particular point is by writing the dy dx and then a vertical line, and the ordered pair we're going to use goes at the bottom. So the x value we know is 1, and one of the y values at a time. So this will be square root of 3 right now. If you remember from part A that we found that dy dx was negative x over y, we can use that. And so the slope at 1 comma radical 3 is going to be the opposite of the x value, so negative 1 over the y value, which is square root of 3. And we can leave it like that. But there's another point that has an x value 1. So the slope at 1 comma negative square root of 3 will be the opposite of the x value over the y value. negative square root of 3. And canceling the negatives will leave you with 1 over square root of 3. Now if you look at the picture, the point 1 comma square root of 3, we can see right here that the slope is positive, and that matches up with this idea. Whereas on the top one, at 1 square root of 3, right here, you see the slope is negative. So it makes sense that that's the slope for that tangent line. A moment ago, we found the slopes of the tangent lines where x equaled 1. In this part of the question, we're finding the equation of each of those tangent lines at those 2 points. So we have 2 answers to this question. First, we have the point 1 square root of 3, and we already found that the slope was negative 1 over square root of 3. And we also have the point 1 negative square root of 3, and there the slope was positive 1 over square root of 3. Now to write the equation of a tangent line, we should use point-slope form. That's the easiest one to use because we have both the point and the slope. So if you recall point-slope form, it's y minus the y value from the point equaling the slope times the x minus the x value from the point. So using that on each of these situations, for the point 1 comma square root of 3, we have y minus the square root of 3 equals, and the slope is negative 1 over square root of 3, multiplied by x minus the x value from the point, which is 1. And for the second point, we have y minus negative square root of 3, which we'll fix in a moment. And the slope is 1 over square root of 3, and it's getting multiplied by x minus the x value from the point, which is 1. The only thing left to do here is simplify the right side to y plus square root of 3. So these are the 2 answers. These are the equations for the 2 tangent lines that we found. Now we'd like to find the points on the curve where the tangent line is horizontal or vertical, not at the same time. Graphing our circle again, we can probably tell visually where these locations are. The horizontal lines appear to be at the top and at the bottom, and the vertical tangent lines appear to be on the left and on the right side of the circle. We can probably find those points just from the picture, no problem. But if the picture was more complicated and not as easy to tell where those points are, we should still rely on calculus to find it. So what we need to understand here is that a horizontal tangent has a slope of 0. That means that dy dx has to equal 0. So if a horizontal tangent line has a slope of 0, and we knew that dy dx was negative x over y, think about when that result might come out 0. If you understand fractions, you'd know that every fraction that ever equaled 0 equals 0 only because the top equaled 0. There's no other way to get a fraction that equals 0 other than the numerator equaling 0. So if this result is supposed to equal 0, that means that negative x, the numerator, has to equal 0, or that x equals 0. And then plugging in 0 into the equation in green, we have 0 squared plus y squared equals 4, and that'll lead us to y equals plus or minus 2. And that agrees with our picture, because here we have a point at 0, 2, and down here we have a point at 0, negative 2. And for the case where the tangent line is vertical, a vertical tangent means that the slope is undefined. And a fraction is going to be undefined whenever the denominator equals 0. So that means the same thing as negative x over y is undefined, which happens only when y equals 0. And just like before, if we plug in 0 for y this time, we get x squared plus 0 squared equals 4, and that leads us to x equals plus or minus 2. And you can see on the graph that this point is negative 2, 0, and the one on the right is positive 2, 0. That agrees with the work we did. I'll reiterate that we were able to see these answers from the graph. That's because this relation is fairly straightforward and basic. If the relation was more complicated and we didn't know much about the graph, doing this work is how you would find out about the graph. You could place these tangent lines and then understand that the actual relation would be fitting in and having to conform to these little tangent lines that we found. The next part of the question is going to ask for the second derivative of y. And since we haven't discussed that before, let's take a minute. Remember that if we start with some quantity y, and we take the derivative of it with respect to x, that gives us dy dx. Now the second derivative means that we're going to take the result of the first derivative and take the derivative again with respect to x of whatever we got for the first derivative. So dy dx, we're taking the derivative of that result with respect to x. So we took the derivative of y twice, and both times it was with respect to x. It is possible to take the derivative with respect to x the first time and then with respect to a different variable the next time. But we won't do that here. That's reserved for a multivariable calculus class. But the point is that this result here is written in a bit of a funny way. We write the d with a little 2 up here and then a y. That 2 indicates that we took the derivative twice. And then on the bottom, we want to indicate that we took the derivative with respect to x both times. So we put the d here, but now the 2 goes on the x. A lot of people want to read this as squared, but nothing got squared here. This is an indication of the order of the derivative. So the way you read this expression is the second derivative of y with respect to x twice. Don't say squared. Now let's actually do this in a problem. So if this was a fresh question and we sought to find the second derivative of y with respect to x twice, and we hadn't done anything yet, the first task would be to find the first derivative and then take the derivative with respect to x of the result we got. But we already found the first derivative in part A. If you recall, we found that dy dx was negative x over y. And so now, to take the derivative of this again, we need to take the derivative of both sides with respect to x. The left side is what we write as the second derivative of y with respect to x twice. But on the right side, we have some work to do. Now, since we're taking the derivative of a quotient, we have to use the quotient rule. So low is the denominator, is y, times d high, which is the derivative of the top, so negative 1, minus high, which is the top, negative x. D low is the derivative of the bottom, and remember, the derivative of y with respect to x is dy dx. And then we take the whole thing and divide by the denominator squared. Now here comes the fun part. We want the second derivative to be in terms of x and y. But there's an extra piece in here that says dy dx. So we need to get that thing out. This dy dx we've already found right here. So we'll replace dy dx with negative x over y, and then simplify this new expression. So on the top, we have negative y. And then for the next piece, we have 3 negatives, so they multiply to a negative quantity. And we have x times x, so x squared, and that's also divided by y. And the whole thing is divided by y squared. We typically don't like having fractions within fractions, so in order to clear this little y denominator here, we'll multiply the top and the bottom by a fraction that equals 1, y over y. This leads to negative y squared minus x squared over y cubed. A lot of people will stop here, but there is something clever to notice. Recall that the original expression we were given was that x squared plus y squared equaled 4. You may notice that the top is just the opposite of x squared plus y squared. With a negative distributed through, you'd get the numerator of this fraction. So really, the numerator just turns out to be negative 4, and we're dividing it by y cubed. And that is the final expression for the second derivative of y with respect to x twice. So it turns out that the value of the second derivative only depends on the y value, not the x value. As you learn a little bit more calculus and the physical interpretation of the second derivative, we can analyze this further. But for right now, we've answered the question that was asked, which was to find the second derivative. Now, this problem that we did here is a typical classroom problem, and you'll find it in textbooks. In the next video, I'll show you something similar that actually appeared on the AP exam, and we'll learn how to navigate those kinds of questions. It'll be on the same topics, but the way they phrase them can be a little more tricky and require more critical thinking. So we'll do that next. See you soon. I hope you enjoyed this video. See you next time.